So the last presenter is Antonio Zecchino, is also from EPFL. Antonio was born in Padova, in Italy. He received the Bachelor of Science in Energy Engineering and the Master of Science in Electrical Engineering from the University in Padova in 2012 and 2015, respectively. In March 2018, he got his PhD degree in Electrical Engineering at the Technical University of Denmark, ETU, on electric vehicles modeling for a proactive integration in the power system, and is currently a postdoc researcher at the Distributed Electrical Systems Laboratory at EPFL in Lausanne. And his research interests are control of grid-connected utility-scale batteries for optimal exploitations of renewables and development of vehicle-to-grid technologies for electric vehicles. Thank you, Antonio. I leave you the floor and good luck with your presentation.
Thank you, Fabrizio, for the introduction. I hope you can see my screen and you can hear me.
Yes, everything is good. Thank you.
Very good. So good morning, everyone, and thank you for attending my presentation on battery energy storage systems control for the concurrent provision of multiple grid services. I am Antonio Zecchino, postdoc at the Distributed Electrical Systems Laboratory at EPFL, Switzerland. And the work I am presenting has been a joint effort by all the co-authors, namely Dr. Yuan, Professor Sossan, Professor Cherkaoui, and Professor Paolone. Within the context of the overall process of decarbonization of the electrical power system, traditional generation plants are displaced in favor of renewable-based generation units, which of course, due to their stochastic nature, are depending on the primary resource of energy, such as wind or sun. This is raising issues at the operational level, both at the distribution level and transmission level. For the transmission level, the transmission system operator, or TSO, has to maintain the balance always between generation and consumption. So this increasing fluctuation nature of the generation poses challenges in terms of speed and amount of primary reserve for the control. Regarding distribution grids, distribution system operators are seeing their distribution grids affected by local technical issues such as component congestion or large voltage deviations. Within this framework, the H2020 European project OSMOS aims at investigating the option of exploiting controllable resources such as battery systems in order to provide multiple ancillary services at the same time, simultaneously. In this work, we have been focusing on the provision of primary frequency control and voltage magnitude control, which traditionally are proposed, are achieved via myopic droop controllers that operate in a myopic way, thus without considering the influence of the grid and asset statuses at the point of the actual service delivery. So the overarching question that we have asked ourselves within this work was, is a flexible controllable unit as a battery system capable of providing the expected grid service under possible grid and asset constraints? So in our work, we have tried to address these questions by means of proposing an innovative control approach for the estimation of the actual BESS capability during the operation, and by means of experimentally testing on our campus with a utility scale battery. In particular, in our study, we have utilized the actual capability curves for the power converter of our experimental setup at the EPFL, which, as you can see on the right, can vary as a function of the AC voltage and the battery DC bus voltage. The proposed controller is capable of predicting what may be the grid and battery statuses for given active and reactive set points calculating during the period where the service is provided, and then send this set point to the converter, sure that this will fall inside a feasible region. Typically, in fact, myopic applications, when setting a set point out of a capability of a converter, the converter will immediately trip, go into error, or they will simply set zero active and reactive set point, thus falling in a situation when the service is not delivered. In our case, we can assure that the service is fully continuously delivered by setting the closest possible feasible point. The scheme in this slide represents the conceptual framework of the controller. As you can see, initial alpha and beta droop values are used to compute the initial active and reactive set point that will be actually the input of our optimization controller. In fact, this set point will be compared with the corresponding feasibility region for that particular real-time status of the battery and the real-time status of the grid. So, with our proposed method, we can predict the AC and the DC voltage in a parametric way, and we can pick the corresponding correct capability curve, and finally sending the calculated active and reactive set point to the battery system. From this slide on, we propose the mathematical formulation in detail with step-by-step description for each phase. We start with the definition of the classical Drup-based controller for primary frequency and local voltage control, which compute the desired battery active and reactive power for given frequency and voltage deviations from their reference values. Of course, the provision of the service is maximized by the maximization of the Drup constants, alpha and beta, for given maximum values of P and Q that are given by the installation itself. And that will be set for the maximum deviation of the input variables. In our case, we have been using historical measurement acquired with P-class phasor measurement unit installed in our medium voltage grid in our campus. In particular, on the one hand, we have considered the maximum deviation of the frequency from the 50 Hertz reference value, taking place with a standard deviation of 3.3. With a factor 3.3 for the standard deviation, meaning that only the 0.1% in only the 0.1% of the cases we will be experiencing the maximum deviation of frequency, thus the maximum corresponding provision of active power. This rather strict assumption is motivated by the requirement from the grid code by the National Transmission System Operator in Switzerland, Swiss Grid, that requires that the quality of the supply of primary frequency control power has to be as a maximum tolerable time of 0.1% of the tender period for which the regulating power cannot be delivered without running into penalties. That's the motivation of this 3.3 factor for the standard deviation. On the other hand, the less strict requirements regulated the quality of the supply for the local voltage control. In this case, we were a bit more relaxed in the choice of these factors, so we decided to pick one, which was guaranteeing a coverage of about 70% of the cases. So in this way, we could finally calculate the initial Drup values, alpha and beta, for the primary frequency control and the local voltage control cases. And as you can see in the table, we have defined these values for different C shrink factors. This factor reflects the total available power that the grid can expect from the system. In fact, for battery system applications, a peculiarity is the modularity of the system, meaning that the system can be operated with a reduced number of strings configuration. For example, in our particular case, we have a total number of 9 strings, but as you can see from the bold values, we have used a configuration with 7 strings. In fact, all the experimental results I will show you later on will be based on this setup. The formulation, of course, considers the selection of the capability curve as a function, as I said, of the AC grid voltage and the battery conditions, such as state of charge and DC bus voltage. So we extracted the piecewise interpolated lines for each curve, and we could obtain the coefficients for the different DC voltage and AC voltage conditions. And these curves are used as constraint in the computation of the PQ set points. Note that H is a complex constraint since it is built from a circular constraint on the apparent power and 2 box constraints on the active powers. As mentioned before, the estimation of the battery status is of utmost importance and is obtained by including the constraint that is reported here based on the equivalent 3-time constant model or TTC model. The reference circuit for the TTC model is reported in the slide, and the resistance and capacitance parameters are included in the table. They have been obtained with a dedicated test that was based on a pseudo-random binary sequence PRBS, specifically a 2-level square wave with on-off periods of normally distributed random durations, capable of exciting a wide range of system dynamics. with this model identification test, we were able to define resistances and capacitances for different ranges of the state of charge, as you can see in the table. So during the real-time operation, according to the state of charge that was calculated for the battery in that conditions, we could have an equivalent model of the battery itself, thus predicting the DC voltage of the bus. As I said, the state of charge is of course extremely important as well, and this is obtained with the information of the state of charge at the previous time step and from the information of the DC power that is in turn calculated thanks to the information of the initial AC power obtained with the alpha droop and the information of the efficiency. Finally, we also have the constraint that imposes a minimum and maximum limit of the state of charge during the period of the control session. Last but not least, we also need the information of the AC voltage to estimate what is the converter capability curve. And this is achieved via the Thevenin equivalent circuit model as expressed by the constraint on the slide. The prediction of the AC voltage at the low voltage side of the step-up transformer of the BESS system is obtained by approximating the equivalent impedance of the reactance of the transformer itself. The approximation, in fact, is motivated by the fact that the rated power of the step-up transformer of our installation is of 720 kilovolt ampere and is way lower than the rated power of the transformer of the campus that links the campus to the main medium voltage utility grid. This rated power is for 40 megavolt ampere. Moreover, the lines in between are very short. They are a few hundreds of meters long, thus motivating the choice of this approximation, since the short circuit impedance of the whole grid can be approximated easily with one of these step-up transformer. So finally, this prediction, along with the prediction of the DC bus voltage, enabled us the selection of the correct converter feasibility region. So the overall optimization problem is formulated by reducing the gap between the initial set point and the set point obtained with the models that I previously described. So if the initial set point falls inside the corresponding capability region, then the two final set point P and Q will be the same calculated initially. Otherwise, the closest feasible point will be selected and will be calculated and then sent to the battery. In this way, we guarantee the continuity of the service provision. And just notice that we included the two weight factor, lambda P and lambda Q, that are basically used to prioritize one service over the other, thus the provision of active power over reactive power or vice versa. So finally, going to some results. As mentioned before, we performed some experimental results at our facilities at the PFL campus. The real-time control has been run for dedicated control test with time granularity of 1 second for phasor measurement data acquisition and optimal set point computation. The communication between the battery energy storage system and the proposed controller has been established with Modbus TCP, and all the computation has been carried out in a MATLAB environment. The paper presented a total of 4 scenarios characterized by different combination of alpha and beta droops. In this presentation, I will show you only results for scenarios 2 to 4, which are the most interesting ones, and where we have the increasing values of the droops. Here are some numbers regarding our installation on campus. So as I mentioned before, it has rated the power of 720 kVA and the storage capacity of 560 kilowatt hour. The technology is lithium-ion LTO, so with titanate oxide cells. And the configuration has a total number of racks of 9 racks. In this particular case, we have used only 7. So the first set of results are for scenario 2, and the droop values are the ones reported on the left. In the top plots, you can see the frequency measured during the test period and the corresponding calculated initial and final active power in red and blue respectively. Actually, only the red line is visible because the two are overlapping. And this is due to the fact that we don't have a so big frequency deviation, meaning that this will cause the initial set point to be already inside the feasible region. Thus, the optimal controller is not activated in the first place because the initial set point was already in a feasible point. So only a check was performed. On the bottom plot, similar consideration can be done. In this case, again, the initial and the final reactive power profiles are overlapping due to the limited voltage deviation and the implemented beta value. In case of over voltages, negative reactive power is provided. In fact, it has a negative value, and the BESS is behaving as an inductor. On the other hand, if the condition was under voltages, then the sign of the reactive power would have been positive, and the BESS would have been behaving like a capacitor. Definitely more of interest are the results for scenario 3, where we can see that we have a higher alpha droop that made actually the controller activated in the first part of the test period. And we can see, in fact, that the values at the edge of the feasible region were set, meaning that the frequency service was not performing as desired, although the maximum power was still provided to partially support the grid. On the right, we have a figure that maps the operating points before and after the implementation of the proposed optimal set point calculation. You can notice that thanks to the proposed method, the points falling outside the feasible region have been retrieved to the edge of the light blue curve, assuring thus the continuity of the service. So it's important to stress out that without this controller, these red dots falling outside the feasible region would have made the converter trip or just providing zero power. Similar considerations are valid for the scenario number 4, where even more aggressive droops are used. In fact, we can see that for almost the whole duration of the test, the initial set point are falling outside the feasible region, but still we could manage to provide a continuity of the service delivery. Finally, it is relevant to quantify the amount of regulating energy that was actually provided during the regulation session, which is the values in blue, which are the values in blue, and to compare it with the energy that would have been delivered without our optimization strategy, which is in red. And of course, a comparison with the ideal case of unconstrained BESS power converter, which is in black. So for the primary frequency control provision, we have quantified the concrete effects of the proposed controller during a real-time control period of duration T, as described by the equations. And the quantification reported in the table shows that there are no differences in case of scenario 2, as I mentioned before. But for scenario 3 and 4, it can be noticed that by using the proposed control approach, the continuity of the service delivery is guaranteed. And this is guaranteed for more than 75% of the time, even with extremely high droop as in scenario 4. But for example, for scenario 1 and 2, where this 3.3 sigma factor in order to comply with the Swiss grid regulation was included, we were sure to be able to provide a service with a continuity factor of 99.9%. To conclude, the paper has proposed a BESS control framework for the optimal provision of concurrent power system services, namely primary frequency control and local voltage control. The proposed controller considers the working condition of the AC utility grid as well as the battery DC voltage in order to be aware of the actual capability of the employed power converter. The experimental test on a commercial utility scale battery showed the capability of the controller to enable primary frequency control and local voltage control within 1 second time rate. An experimental test showed that the proposed control algorithms guarantees the continuity of the grid service provision with high droop and low values of the undelivered energy. And thank you for the attention to everyone.
Okay, thank you very much for a very comprehensive presentation. So we have a few questions from the audience. So, all right, so Matt Dakin from Newcastle University is asking that the capability curves vary of the converter vary as a function of the AC voltage.
Yes.
And presumably the capability curves change as a function of Q when the system is connected to a system. So I'm not sure. So maybe you can read the question and see if you
I actually have a small technical issue, Fabrizio. I cannot find the question and answer panel, and I cannot even see the Zoom. I can just see
I guess what Matt is okay. So it's clarifying now. I think what Matt means is that if I'm interpreting right, okay. Question is that, of course, when the power converter will inject some reactive power in the network, then the voltage of the node will be affected. So I think Matt is asking whether you are modeling somehow these sort of closed loop interactions between the injection of the reactive power of the converter and the voltage of the node. So are you accounting for that?
Yes, thank you very much for the question. It's very relevant. Yes, in our model, we have considered the estimation of the AC voltage with the equivalent model of the grid. And this actually took into account the initial set point of the active and the reactive power that we calculated with our input variables. This means that we are actually already taking into account the effect of the provision of our active or reactive power in terms of influence on the local voltage. And this, in fact, is taken into account in this estimation, so that when we directly consider the estimated AC voltage for the selection of the capability curve, we embed the influence of it on the local voltage at the point of connection.
Yes, okay, thank you very much. I think we don't have... I think this was a very important point in a way. That certainly, I think the method can certainly account for closed loop interactions between the converter and the grid. So it was a very good question. So yeah. I don't see any other questions concerning your presentation. So since we are also 9 minutes late, I think we can close the session here. It's late because it's probably my fault, it's not yours, Antonio, so no worries. Okay, thank you very much to all the presenters and to all the attendees. I think it was a very interesting session with very good presentations. And yeah, I think if to those in Australia, I wish you probably a good night, and to those in Europe, probably bon appetit. So have a good continuing of your day.
Thank you. Thank you, Fabrizio.
Thank you very much.
Everybody.
Take care. Bye-bye.
Bye.